And we're gonna get started here. So these are my memes and gifs of the week. A surgeon and a plastic surgeon. Ha, ha, ha. Popular streaming subscriptions. We can add university now because it's expensive as hell. And everything's online, so woohoo! And then last but not least, for my procrastinators, constantly ask ourselves, why are you like this? Which also segues into the fact that this week we are wrapping up our content that will be on the first exam. So fun stuff, but there's going to be a review next week, which is still optional, but I'll have kind of like a practice test for you guys that we'll go through. I don't know if we'll get through the whole thing during the class period, but we'll get through as much as we can. And then part of that review, I've randomly selected different questions from that. And then they go into a review quiz, which is optional for you guys to take for extra credit. So feel free to use that opportunity if you want to. And then the following week, we'll have our exam. So I'll send you guys updates on what to expect on the exam. Most of that will be covered next Monday, so you kind of have an idea of the layout and types of things that we'll be doing. But just so you're thinking ahead, today we are talking about measures of variability. So last time we kind of finished with measures of central tendency. Now we talk about not only what those central tendencies are, but how spread out is the data around those central measures, right? And then we're also going to talk about how all of that relates to the normal curve, which we've kind of already commented on. But this week we're going to add another way to calculate percentiles using a z-table. So if any of you have taken like a rudimentary statistics class for GE or something, you might have gone over some of the z-score stuff before. If it's been a while, then we get a refresher. If you have no clue what I'm talking about, then we named a table after a letter and it's useful in statistics. So here we go. All right, we'll start with measures of variability first. We can kind of move through this part pretty quickly because several of the equations that we're going to be talking about, you guys have actually already seen in some of our activities. So that's cool. But these are the different measurements that we're going to be using. You guys have looked at range, interquartile range, and standard deviation as far as procedures go, but we haven't talked about them conceptually yet. So that's kind of what the point of today is, to tie the two together. But generally, variability just means how far apart our data is or how spread it is, okay? Like butter. But we can visualize the spread of data around a central measure. And so that's why usually when you read a research paper, it's like, this is the mean plus or minus the standard deviation, right? So what is the central tendency, and then how far or how spread out is the data from that central measure? Okay, this is just representing what different spreads might look like, right? So this would be a larger standard deviation, meaning that the first standard deviation is further away from the mean compared to something that maybe has a smaller standard deviation, okay? But we'll go through each of these one by one. We'll start with the range first. So this is probably the simplest one to calculate. We start easy and we get harder as we go along, right? So the range is literally the biggest number in your data set subtracted, and then you subtract the smallest number, right? So it's a very quick, easy calculation that we can make. Super nice for us, right? It's also a rough estimate of the spread of data. And we say rough estimate because we know, at least last week, we talked about outliers or kind of extreme values that could exist within a distribution. And so if, say, and this is where we see if it works. Okay, I think, do I do this? I did it right. Okay, so if we have, let's say we collected a group of students and we measured their ages, right? Let's say we're picking people from this class, right? Maybe we have a minimum age of 20 and we have a maximum age of 35, okay? So in that case, we would calculate our range by saying 35 minus 20, right? And that would give us a range of 15 years. Well, it was almost nice, but anyways, we have a range of 15 years, okay? So this gives us a good rough estimate of how spread the data is. However, we don't always like this method in terms of statistical analysis because maybe there's only one 35-year-old in this class, but the next oldest age or next oldest age going backwards, right? Maybe is 23, okay? So in that case, our range would be 3 years, okay? Which is very different from 15. And the reason why we got this extreme difference is because of this extreme score, right? So we get a rough estimate of the spread of data, but we don't always get the big picture just because if extreme scores are involved, they dramatically skew what the range actually is, right? Because we're going from one end of the spectrum to the other end. So you have to use it with caution. Any questions on range? I feel like usually this one's pretty easy. So we'll move on, okay, to our interquartile range, which you guys got to experience in the activity last week, okay? So the interquartile range, if any of you guys have ever heard of box plots before or box and whisker plots, they usually look something like this, where you have a box, there's a line somewhere in the box, and then there's whiskers off of that. Okay, the interquartile range is this area here. Okay, so basically what we do is we split our distribution up into 4 parts, okay, or what we call quartiles. Quartile 0 technically doesn't really exist, but we call that wherever the minimum of the data is, right? Or where the 0th percentile would exist. Okay, so for sake of this example, we'll call this Q0. Okay, if we move along, we would expect the 25th percentile to be what we call the Q1. I should have turned off notifications or put do not disturb on, which, no, I can't do. Never mind. I'm just gonna undo that line. Maybe not. Anyways, so Q1 or quartile 1 is where the 25th percentile would exist. Q2 is where the 50th percentile would exist, so that's the measure or the central measure of our distribution. Q3 we say is at the 75th percentile, and then Q4 again should be about at the 100th percentile, but often we just say it's the maximum of the data. So what the interquartile range does is it takes the center, right? So we get the center 50% of the data, right? So it's nice, different from the range because we kind of exclude any potential extreme scores on the outside, but we still get a relatively good idea of how spread out the data is within the majority of the distribution, right? Or within the 50% where we should have a majority of our distribution. Okay. So I think I have one more slide on this. Right, so good indicator of the majority of the data, not influenced by extreme scores. It's often used with ordinal data, so when you have a rank order type values, right? Or we could also use it with highly skewed data, purely because of this extreme score idea, right? Interval data is also another good one to use the IQR for, largely because 0 is not considered a non-score, if you will. So if we're kind of ranging in a like around 0, for example, let's say the minimum of our data is -10 and the maximum is 30, right? If we want to find the range between those two values, it kind of messes with us a little bit, right? Because then we're like, oh, well, the range is 20, or is it, right? Because the negatives are introduced. So using the IQR is kind of helpful for when we have situations like that, when there's both positive and negative values. It just gives us an idea of how far spread out our central values are within the distribution. Okay. Any questions on the interquartile range? Cool. Okay. So then we go into variance, which some of you may have heard of before. Okay. The book defines this as the average squared deviations from the mean. Okay. So deviation just means, like, think of a juvenile delinquent whose deviant behavior gets them in trouble, right? They're acting away from the average. Okay. So deviation just is indicating some distance from the mean, which is our measure of central tendency in this case. Okay. So you don't need to know this formula. You do need to know how to calculate the interquartile range and regular range, but variance, we can calculate this in Excel. We don't usually calculate it in Excel because we typically use the derivation of variance, which is standard deviation. So this is kind of just more a conceptual thing. But this is the formula, right? Sigma means summation. So this numerator is telling us what we call the sum of squares. Okay, so what it does is what's in this parentheses, this is x being a raw score. Mu, if we're using a population, mu is the mean of the population. And then we take the difference between whatever this raw score is from the mean of the population. That tells us how far away that raw score is deviating from the mean. We square it to eliminate influence of negative values. So that's what we call the sum of squares. Add up the differences from every single one of your raw scores, and then we divide it by the sample size, and that tells us the variance. Okay, so I have an example of this because using words to describe formulas sometimes isn't always easy. Okay, so let's say that we're given this information. We've got our variance formula, we've got a mean, and we've got a sample size. Okay, and then I've given you guys a list of X values, which would be raw scores within some distribution. Okay, so with the first part of this is we have to look at the distance or the deviation of each value from the mean. So we would literally just do 12 minus 21, and then we would square that, right? So you should get a list of values, right? taking the difference, squaring, or taking the difference. So I skipped ahead of myself. We're just taking the difference, right? Then we would square all of those values, okay? And then we would add all of those squares together. So you see that there's a spread in both the positive direction above the mean as well as below the mean. Squaring these values gets rid of those negatives and instead kind of just tells us what's the general distance that we see of deviation away from the mean, okay? So after we get the sum of squares, that 292 value is from the numerator. Then we have to divide it by the sample size, and then we get 36.5, okay? So I don't know what units we're working with. Let's say we have inches, right? And someone maybe did a jump or something, right? And we want to know what does variance mean in terms of the units of measurement, right? Variance, that 36.5 for this given example, takes on the units of measurement that you're analyzing, okay? So we would say, oh, the mean exists at 21 inches for these people jumping, right? And the variance is 36.5 inches. Okay, again, that's more of an absolute difference or absolute deviation from the mean. So it's not indicating a direction, right? But that's kind of, if you want to tie it to 312 terms, it's like absolute error, pretty much. Okay. All right. So from variance, right, it's generally describing a deviation from the mean. If we take the square root of the variance, that's how we get standard deviation. Okay. And what standard deviation does, if you guys remember from, regular algebra days, whenever you take a square root of a certain value, right, the result could either be positive or negative, right? So the square root of 4 can either be plus or minus 2. Okay, so this is nicer in terms of when we're reporting statistical information, just because we can say there's a given mean that we've calculated for a sample, and the deviation away from that mean is approximately this value above or this value below, right? And then when we talk in terms of how many standard deviations away, those are multipliers of the value that you actually calculate. And we'll go over an example of that because I realize, again, wording, bleh, right? But generally, it's just the variance equation with a square root around it, right? This is baby sigma, right? So this is big sigma. Baby sigma represents, or lowercase sigma. I think baby sigma sounds better. But that lowercase sigma is going to represent a standard deviation for a population, okay? So I just want to clarify. Baby sigma and mu are population notations. I try to keep my notations straight in this class. So if for some reason I mess up, just know for everything we do in this class, you will always be using sample calculations, okay? So that usually would include, instead of mu, you would have an x bar, which, if I can get my pen, x bar is that, right? It's an x with a bar over top of it. Okay, pretty simple. But that's how you'll see me refer to means, and then usually standard deviations, I just write SD. Okay, but we still have this idea that we're taking kind of the absolute variance or absolute deviation from the mean, and then we're just square rooting that into plus and minus directions. Okay, so we still understand what the spread of data is around a measure of central tendency, but I think standard deviation allows us to look in multiple directions compared to variance, which is more of an absolute measurement. Okay. Any questions so far? Okay. So there is a distinction I was already mentioning between samples and populations, right? And we talked about this in the first lecture where samples, we use samples to calculate statistics, and we use populations to calculate parameters. And usually we don't have information on the entire population unless an extensive amount of data has been collected over either a long period of time or somehow we were able to track down every single person that would live within that population and we were able to measure them, which is nearly impossible. But because we can't always calculate or use population sizes and we're going off of sample sizes, that requires that we have a correction factor, okay? Because we like to assume that we have a representative sample of the population, but I mean, if you take, maybe let's say your population is approximately 1 million people, but your sample size is 30, right? How do you draw conclusions of 30 people onto 1 million people? Okay, and that's why we include this thing called degrees of freedom. Okay, so this is super important as in terms of being a correction factor for our calculations, and degrees of freedom will show up in different ways. I'll just leave it at that for now because you'll see in coming weeks, but usually, well, it's dependent on the number of samples typically and or the number of variables that you're working with. But degrees of freedom, basically, we kind of just start off in this class saying n-1 because that's the degrees of freedom that are inserted automatically into the standard deviation and variance calculations. So we'll just start with that as our example. But we need the correction factor because sample size is not always equal to the size of the population, right? So you can see we can take pretty much the same calculation, right, that we started with the variance and with standard deviation, and instead all we do is instead of n, we put n-1. Okay, so I'll show you the comparisons, right? 36.5 and 6.04 were the variance and standard deviation values that we got from the previous slides, assuming that we were working with population data, which we know isn't true, but use your imagination, okay? When we apply the degrees of freedom, right, in this case, which is n-1, you can see that the variability increases in both the sample measurements for variance and standard deviation, okay? So you think, oh, larger variance is bad, right? But that's the point of the correction factor, is we're kind of just saying, we know taking a small sample size is going to have some degree of error, right? Because we can't assume that we've collected every single representation of the population within that sample. And so by saying that there's some degree of error, we're expanding our variability such that we can kind of say this is more or less what the population would actually look like in terms of variability. Okay, so that's why you usually want larger sample sizes in your in research that you conduct, just because if you already have more variability, the larger your sample size is, the closer these sample statistics will be to what the population parameters might actually be in real life. Okay. So Does anyone have any questions on degrees of freedom?
Yeah, I got a quick one.
Yeah.
On the exam, you're going to give these equations, but not put like variance or standard deviation equals
Right.
them.
And actually, these ones I don't give to you guys because anytime you calculate a standard deviation, it'll be in Excel. I just use these to show the representation of the degrees of freedom primarily because they show up later in the semester. But yeah, if I gave you guys like, we can do an example of a previous slide, like the interquartile range, you would just get Q3 minus Q1 would be an example of
Oh,
how,
okay.
yeah, of
Perfect.
how you would get those equations. But I probably won't give you the variance and standard deviation just because I don't require you guys to manipulate those. It's primarily more just the conceptual side of things.
Thank you.
Uh-huh. All right. So our last measure of variability is the coefficient of variation. Okay. And if you guys remember, last week I mentioned a term called standard scores. Okay. So remember, standard scores allow us to, they're standardized, right? So they allow us to compare either different samples that don't come from the same populations, or they allow us to compare different units of measurement to each other. Okay, so a coefficient of variation is another type of standard score. So far, our standard scores we have used so far are percentiles and coefficient of variation. Okay. But coefficient of variation is a way of standardizing or normalizing standard deviations that have different units of measurement. Okay. So if I was calculating a person's mass in comparison to their VO2 max, in comparison to ground reaction forces in a in walking. I don't know, right? I'm pulling these examples out of my butt, but you're gonna get my point. We have a whole bunch of different measurements that have different units of measurement, right? And we can use whatever those measurements are, information with regards to that data, right? By taking mean and standard deviation, which you guys know how to calculate now, right? Via Excel or SPSS, since that was part of last week's activity. We use characteristics of each set of data, we turn it into a percentage, and then we have a standardized representation of the spread of data, right? So maybe I have my mass variability in my sample is like 12%, right? And my VO2 max is 30%. And I don't even remember the other variable I gave you. But, right, you can see we have these percentages and then we can compare those percentages to each other. So here's actual mathematical data. I should have just put this up to begin with. But in this case, we can evaluate max or VO2 max and peak power output, right? Given that we have a sampled set of data, we can calculate the mean and standard deviation, okay? And this is a good example of one of the places where I put mu, probably because that's what the book put when I made these slides forever ago. But just think mu or x bar, the mean is at the bottom, standard deviation is in the numerator in this equation, okay? So we've calculated these certain what do I want to call them? Just mean and standard deviation. We calculate the mean and standard deviation for each of our samples or sample, because you could have collected this data from a single sample, right? But we can do 6 divided by 60, right? And that would give us a coefficient of variation of 10% for our VO2 max. And then if we did 200 divided by 1400, right, that would give our power output a coefficient of variation of 14.3%, right? Obviously, we're multiplying by 100 to get the percentage. But the way that we evaluate which of these is more variable than the other is based on the actual quantitative value of the percentage. So a lower percentage means that there's less variability relative to whatever the other variable you're looking at, right? In this case, we would say VO2 has lower variability than the power output data, okay? Does that make sense?
Yeah, we're good.
Awesome. Okay, so that's it. That's our measures of variability. Super simple. Okay, so range, interquartile range, variance, standard deviation, and coefficient of variation. And the two standard scores we've talked about so far are percentiles and coefficient of variation. Okay, we're gonna add
So then
two more on top.
conceptually, you want to figure out when and why to use those?
Yeah.
Okay.
Conceptually, why?
Wait, I'm sorry. Sorry.
Oh, go ahead.
No, I was going to ask how you got 14.3 again. Sorry.
So you do the standard deviation. So for power output, it's 200. And then you would divide it by 1400. And maybe my math was wrong. Or maybe I changed values from previous semesters. But it should be 200 divided by 1400 times, times 100. And then you get that. I don't know if you can see my calculator. Yeah. But yeah, that's how we got it.
Perfect.
So in terms of what you actually have to calculate, you'll do examples in your activity this week, but mainly it's range because that one's super easy, interquartile range, standard deviation, and coefficient of variation. Variance is just a conceptual example. Okay. But it's good to know when you would want to use these as well as how to actually calculate them. Okay. So the second section of the lecture is on the normal curve. And you're like, why are we looking at the rock? Because there's a bell in the GIF, that's why. Okay, so the normal curve is our bell curve or our normal distribution. Okay, and ideally, like we've talked about before, the normal distribution is going to have equal frequencies of data on both sides of the mean. The mean we're saying is in the center. Okay, so in a perfect world, this distribution is symmetrical, where the measures of central tendency are all equal to each other, right? So mean, median, and mode are all at this center point. Okay, but we've already done frequency distributions, right? And we know that typically, if they were normally distributed, they should look something kind of like that, right? So we can just overlay a smooth line on top of it, and now we have our bell curve. Ding, ding. Okay, I'm really dumb, but we accept it and we move on. So the normal curve has this thing called the empirical rule. It's also known as the 68, 95, 99.7 rule, but I think empirical rule is a lot easier to say. The numbers, however, represent different percentages of data that lie within specific regions of the curve. So this S down here, just imagine that is standard deviation, because that's what it's supposed to stand for. Okay, the 0 in the center is where our mean is located. And then going away from the mean, we have +1, +2, and +3 standard deviations from the mean. Go in the other direction, we have -1, -2, minus 3 standard deviations from the mean. Okay, what the 68 or 95, 99.7, where these numbers come from, are what percentages lie within plus or minus 1, plus or minus 2, and plus or minus 3 standard deviations. So if we put our little graphics on here, right, 68 is teal, so that's this bracket between plus and minus 1 standard deviation from the mean. If you add up these percentages, 34% and 34%, you should get 68%. So the empirical rule says that 68% of your data should be between the first standard deviation above and below the mean. So then you can guess, what does 95 represent? The percentage of data that exists between plus and minus 2 standard deviations from the mean, right? And then 99.7 should be plus or minus 3 standard deviations. And you can calculate 95, right, from adding 13.59% twice plus 34.13% twice, right? That should, the sum of these 4 values down here should give you 95% or approximately 95%. If you add on, right, the only difference between this yellow bracketed area and the red bracketed area is about 4%. So that's why we go from 95 to 99%, right? And then anything past 3 standard deviations, there's usually hardly any data that exists out there unless you potentially have an extreme score outlier, okay? So in terms of the empirical rule, it's important for us because 95%, some of you guys might have heard of, we have an alpha level of 0.05 or we have 95% level of confidence. That's where that 95 comes from. Because typically we accept results on the basis that if we're comparing samples to each other, one sample mean within another sample mean, right, that's no further than plus or minus 2 standard deviations from each other would be considered from the same sample. And that probably doesn't make a whole lot of sense now, but when we get to t-tests, it will, okay? But this 95 is kind of the central concept that the majority of our data lies between 2 standard deviations, right? And anything past that usually is either indicating some significant difference or that our raw score is not normal, either being above average or below average. Okay. So moving on. How do we get to z-scores? Okay, so remember the normal curve is on the basis of, it's built on the basis of standard deviations, right? Standard deviations tell us how far, it's a measure of variability, right? So how far data is spread away from the mean. So we can translate standard deviations into z-scores. Okay, the thing to remember is that standard deviation by itself, when you calculate it, it assumes the units of the measurement that you're looking at, okay? But the actual distance from the mean is standardized, right? So if we had, I'm gonna attempt to draw this in a place that won't impede. I'm just gonna do it down here. Okay, so let's say that we have a distribution, right? And in terms of our mean, let's say our mean is equal to 10 and our standard deviation is equal to 5, right? The way that I just wrote this, those are in the units of the measurement that I collected, right? So when I would build my actual distribution, right, 10 would be at the center because that's the mean. And then we would say 15, 2 standard deviations would be 20, 3 standard deviations would be 25, right? And then we can also count downwards, 5, that would be 0, -5, right? So we can build a distribution by using the units of measurement, but we also know that, where's my cursor? We also know that, oh, I want a different color. Cyan is nice. Cyan is sus. If anyone plays Among Us, I'm always cyan. Anyways, we can also write in terms of standard deviations, right? So this would be +1, +2, +3, or -1, -2, -3, right? So both of these notations are correct, technically, right? And we can think about whatever the units are, right, for our standard deviation. We can just say, well, 15 is equal to 1 standard deviation from the mean in terms of the actual sample statistics that we have, or descriptive statistics, right? In terms of z-scores, we have to use this blue notation to translate to z-scores. So that's what this part means up here. 1 standard deviation is equal to 1 z-score, okay? So 1 standard deviation, 1 z-score. The value of 15 in this distribution is 1 z-score from the mean. It's 1 standard deviation from the mean. So you can kind of see how they're interchangeable. Okay. You do need to know how to calculate this one. Okay. This is the population notation, just because we have mu and baby sigma. This one is our sample notation, because we have x bar, right, which is our sample mean, and SD, which is our sample standard deviation. Okay, so we'll go through some examples of those. Let me first erase this. Okay. And then what we can do with these z-scores is we can use them to calculate percentiles or probabilities. Okay, so z-scores are another type of standard score. So far we have percentiles, coefficient of variation, z-scores. 3 types of standard scores. Okay, I'm making a list because it's important. Also because it might show up on your test. So.
Natalie, can you repeat that one more time, please?
Yeah.
You said it was percentiles, z-scores, and what?
So our standard scores are percentiles. That was the first one we covered. We have coefficient of variation, which is how we turn variability into percentages, right? And then we have z-scores. That's what we have so far, okay? So what the heck do we do?
I have a question.
Yeah, go for it.
Wait, so you said the z-score formula to the left, that one's used for sample, and then the other one to the right is for the population?
So this one is population, this one is sample.
Oh, okay.
Yeah, so mu, yeah, anytime you see Greek letters, think population. So usually mu and sigma are indicating that you have population parameters that you're calculating. And then when you see English letters or alphabet letters, those are sample. Because we're not as sophisticated as the population. Yeah. Okay. All right, so z-scores translate, or we use a z-table, and I know these numbers are super small, but we'll zoom in on this for an example later. We have 2 different z-tables. One of them is positive, the other one's negative. Okay, so that makes sense because you have positive and negative standard deviations, and a standard deviation is equal to a z-score. So what these tables do is they tell us the percentile or the area under the curve at a given z-score. Okay, so when you look in terms of, if I bring back our bell curve, right, we expect that 50% of our data exists in this direction and 50% of our data exists in the other direction. Okay, so the negative z table should have probabilities of 0 to 50, or 0 to the 50th percentile, and positive z-scores, or their positive table, should have probabilities or percentiles from 50% all the way up to 100%. Okay, so in terms of values or probabilities, percentiles, you can always kind of double check by looking at the actual probability you calculate. Okay, so in terms of the table, how do we read it, right? If you calculate a z-score, maybe it's given to you, maybe you calculate it from your raw score, your mean, and your standard deviation. But whatever that z value is, the first column represents if you have a whole number plus the first decimal place. And then all of these other columns going across the top are going to be kind of your 100th decimal place, if you will. Okay, so if we had a z-score of 1.82, right, that's saying we have some raw score that exists 1.82 standard deviations from the mean, or 1.82 z-scores from the mean. The way we would look that up on this table is we would say 1.8, and then we would go to 0, 1, 2, right? So I'm looking at this 0.02 up here. So 1.82 would tell me I have a probability, and I think I'm saying this correctly. We have a probability of 0.9656, which translates to 96.56%. Okay, and that should make sense, right? Because we know 95% of our data should ideally exist between two standard deviations. So this indicates, right, if we're considering how the z-table tells us, right, it's going to indicate the percentile or percentage of data that is to the left of whatever the raw value is. So not only is it including between kind of that 2 standard deviation area, but extending past that to the end of the distribution. Okay, so I have a bigger visual representation on the next slide, but this is a very important concept to remember, because when I ask you certain questions, both in your activities, on the quiz, as well as the exam, you have to be kind of cognizant of what the z-score tells you, what the percentiles are that you get from that z-score, and then how to manipulate those values based on what I'm actually asking you. Okay, so again, z-scores will give us at some raw score in the distribution, right? Z-scores tell us how far away from the mean that raw score is. And then when we look at the z-table, we're given a probability or the percentile at which that raw score exists, right? And remember, percentiles are always telling us at or worse than a given score. So anything under this curve is shaded. Okay. Which this is a perfect segue into some examples. And let me think about the best way to do this. Okay, I'm gonna stop sharing for a second. And do you guys potentially have your z-scores pulled up in front of you? If this is a yes, no, maybe so. What I'm gonna
Yeah, you gonna ask some questions?
I'm just gonna make up some examples really quick. So what I'm gonna do is I'll put the z-table in the chat so you can open it and look at it as we go through stuff, because I'll be able to see my z-table on my computer, but I cannot assume that you can also see it. So let me end my slideshow real quick. And I'll shift gears to a whiteboard. Okay. Let's do whiteboard. All right. So you guys see a white space? Yes?
Yeah.
Cool.
Yep.
All right. So let's say I love this iPad, you guys. It's so amazing. Okay. I haven't like upgraded technology in like 5 years, so this is huge for me. Okay. So we have this distribution. Okay. And we'll say that did not mean to do that. Zoom back in. Okay. Let's say that our mean exists here, which we'll just say is 0 for the purposes of creating this, right? And then we'll say we have +1, +2, +3 standard deviations, and -1, -2, -3 standard deviations, okay? Somebody give me a random number that's like greater than 20.
27.
Okay. So let's say for the sake of this example, our mean is 27. Okay. And then give me a number that's smaller than 27, preferably like smaller than 27.
4.
Okay. I need to have better word choice sometimes. Okay.
So this would be, we're working with like a sample size here, right?
Yes. Yes. Okay.
And you know that because the standard deviation is not mu, it's SD.
Correct. And
Gotcha.
also the mean is an X bar. So yes. So we can write this distribution in terms of standard deviations, which is what that row is. The other way you can write it, remember, is using your actual values. So if we do 27 plus 4, we should get 31, plus 4 is 35, plus 4 is 39, minus 4, right? We get 19 and 15, okay? So on your exam or quizzes, whenever you're constructing your distributions, just remember you can construct them either way, okay? Standard deviations also translate into z-scores because they are interchangeable when they're in terms of numbers 1, 2, and 3, okay? So let's say that I'm interested in finding the percentile for a person with a raw score of 32, okay? So for the purposes of this example, we say 32 likely exists at about that area, right? If we kind of divided how far away 31 and 35 are from each other. Oh my God, come back. Okay. So we would say X is our raw score and it's equal to 32. Okay, but what does that mean for us, right? I want to know what's the percentile of that raw score, which means I'm looking for any value that exists to the left of 32, right? Because that's what percentiles mean. Any score at or worse than the specified score. So we need to convert this to a z-score if we're going to use the z-table, right? The other method we've used prior to this is when we've got a frequency distribution, but as you can see in this case, we don't have a frequency distribution, okay? And I'll get into specifics on when to use which method because there is a distinction. Okay, but if we look at our formula in our PowerPoint, right, the calculation for a z-score is z is equal to the raw score minus the mean divided by the standard deviation. So we can easily calculate what z would be for our raw score of 32, right? We take 32 minus 27 and divide it by 4. Okay, so
You get like 1.25 or something.
yeah, I'm gonna do my maths because I know it's not an even number. So we get 1.25, which makes sense, right? Because 1.25 should, right? We would expect if our raw score is between 1 and 2 standard deviations that this z-score should be between 1 and 2 standard deviations or 1 and 2 z-scores, right? So we get a z-score of 1.25. What do we do with that? Okay, so this is where we go to our z-table. So based on this z-score right here, right, do we want to look at the positive or the negative z-table?
Positive.
Positive, right? Because it's a positive z-score. It's above the mean. So already, just based on the positive location, right, are we going to expect a percentile greater than 50 or less than 50?
Greater?
We would expect one greater because it's above the mean, right? So I'm going to do a new share just to kind of segue over.
So when you get the 0.8944, that's your percentile? Right, so it'd be 89th percentile? What is that 8944?
Oh, I just saw the chat. It could be. Let's see. Let's see if Aaron is right. I have confidence. It sounds good. Okay, so I'm in my z-table. Let me expand this so it's a little bit bigger. Okay, but we have a z-score of 1.25. So if we go to 1.2, and then we go over to the column that has 0.05 in it. Aaron, you are so right. Everyone applause. I wish I could do reactions, but applause. Yeah, you went ahead, but that's okay, right? So 89.44%, if I switch back to my whiteboard, right, we've got, there it goes. I was like, come on, you're lagging, right? That means that this, I'm gonna erase this real quick. Okay, so this area, this green shaded part, we can list it as a probability as P, lowercase p, right, as 0.8944. I said that right? Yeah, 8944, okay? So as a probability, whenever we're speaking in terms of probabilities, they have to be between 0 and 1, okay? Oh yeah, kitty, this is Boo. Anyways, probabilities are always between 0 and 1. Percentages or percentiles are always between 0 and 100. Okay, so if we multiply our probability by 100, we can get our percentile, which I'll distinguish with the percent sign, of 89.44%. Okay, so we can say that 89.44% lives in this shaded area, or that a raw score of 32 is at the 89th, approximately 89th percentile, given our distribution. Okay, so one distinction I wanted to point out, because I feel like this is one thing that students usually get tripped up on, is they're like, oh, well, what if I'm given a frequency distribution and I don't, because sometimes I'll give you one, sometimes I don't. And sometimes I'll ask you, what is the exact percentile versus what is an estimated percentile? Okay. Exact and estimated are the keywords to look for. Okay. So I'm going to erase this really quick. And this is why I want to make this distinction. So if we're looking at an exact percentile, okay, usually I want whatever the percentile is in terms of the sample that you have. Okay, it doesn't have to be normally distributed. It doesn't have to have any normal shape at all, right? I just want to know, given this frequency distribution, what is the exact percentile? So the shape of your distribution might look like this. It could look like this, right? In the case of an exact percentile, it doesn't matter what your distribution looks like. Your mean is going to be somewhere, right? And we just want to know how many values are to the left of a given value of interest, right? So whenever I ask for an exact percentile, you're going to want to use the frequency distribution calculations that we did last week. Okay, so that's when we look at what is the cumulative frequency at a given value divided by the sample size, or we had that more complex group frequency distribution calculation. Okay, so those would be exact percentiles. Okay, when we want an estimated percentile, whoops, I need to change my pen. Estimated percentiles are when we use our z-scores. And the reason we use z-scores, I'm just going to put z, okay, is because estimated percentiles, or whenever we use a z-table, that is under the assumption that we have a perfectly normal distribution, right? Meaning that 50% of our data is on one side and 50% of our data is on the other side. Okay.
Natalie,
Yeah, go ahead.
going back to like a real life scenario, looking at research, you most likely use frequency distributions, right? Because would your data ever fall like symmetrically exact 1/2 and 1/2?
In my personal experience, I've never had that happen before. I've gotten close.
So then you, okay.
Yeah.
Gotcha.
But that's the whole purpose of z-scores, is like, if you have a distribution and it's relatively normal, which we'll talk about kind of at the tail end of our lecture. If it's relatively normal, we can still apply this whole z-score concept. And
that's just because it's times.
Yeah, it's relatively the shape of what a normal distribution should look like.
Thank you.
So kind of going off that question, like if we were like on the exam and then you said it just wasn't not even close to normally distributed, would we then have to use the exact percentage then? Like using the formulas we learned last week?
Yeah. So whenever you see estimated, you automatically think, I have to use a z-score to calculate the percentile, and I have to assume that my data are normally distributed. Okay, that's like the essential portion of this. You can only use z-scores when you can make that normal distribution assumption. Okay, reason being, I'm going to shift screens really quick, is like we said, in our z-table, right, if this is our positive z-scores, this is starting at the mean, you can see the percentage of values that lie to the left of the mean is exactly 50%. Right? So that's why this translation only works if you have a normal distribution. Similarly, if we go to, where am I? This is the negative z-table, right? At 0, again, we have 50%. And then as we go further away from the mean, our percentages get smaller and smaller and smaller till we almost get to 0. Okay. So again, exact percentile is looking for percentiles using cumulative frequencies and the group frequency distribution formulas. Estimated percentiles, you use z-scores, and you have to meet the assumption that your data are normally distributed. Okay. Now, I do have some questions in your guys's quizzes and whatnot that ask you to identify what percentile of scores might land between two values or that might land above a certain value. Okay, so we'll do an example of those here. So we've got our bell curve, right? And we know that a mean exists somewhere in here. I'm just gonna put, well, we can use numbers. Let's use the same numbers we used before to make it easy, right? So we had 27 as our mean, and then we went upwards by 4. Is that right? 31, 35, 39, and then 23, 19, 15. Okay, so now let's say I want to know what the probability is that within the given sample that I've collected, I get a score, a raw score of 20. Okay. So I can write that, right? I want to know probability of getting a raw score of 20. Okay. So first things first, we say, okay, where is 20 on the distribution? It kind of looks like it would exist here, right? So we need a z-score. How do we calculate that? Anybody?
X minus the mean
X minus,
divided by standard deviation.
exactly. So we would do 20 minus 27 divided by 4. We should get a negative value, which would be expected. And I actually get negative 1.75. Okay, so this is now our z-score, or in terms of standard deviations, right, we're minus 1.75 standard deviations from the mean, minus 1.75 z-scores from the mean, right? So where, if I'm looking up this z-score on a table, what area under the curve am I going to get from that table? The area to the left of the green line or the area to the right of the green line?
Yeah, to the left.
To the left, right? So actually, to clarify, this up here, the original question I asked you guys was, what's the probability of getting a score greater than 20? Okay, so probability of, let me change this slightly. What's the probability that I get some raw score greater than 20? So 20 is like our starting point. And I just noticed someone had a chat thing. Oh, left. Yes, Bree, you are correct. Okay, so my z-score table is going to give me that. And can somebody look up what the probability is under the curve for negative 1.75?
Yeah, it's 0.0401.
0.0401. Okay, so that means this area, right? probability is equal to 0.0401, aka 4.01%, right? But that's not my answer, right? Because I asked, what's the probability of getting a value greater than 20? So
you subtract 100.
what do I do?
Subtract that from 100.
Exactly, right? Because anything or the rest of the distribution is over here. This is what I'm actually interested in, right? And the way that we can get this area is by either doing 1 minus, 1 minus 0.0401 if we're talking in terms of probability, or we can do 100 minus 4.01, right? And that will return what percentage of our data points actually lie in the area that we're interested in. Does that make sense? You can use yeses and nos in your participant responses.
Yeah, it does.
Yep.
Thumbs up. Thumbs ups are good. Okay. So let me give you an additional scenario. Let us do, I'm going to try to make this as clean as possible without having to redraw a whole bunch of stuff. Okay. So we're going to, woo! All right. So now let's say that I'm interested. What is the probability that I'm going to have a raw score, X, but this time, let's say it's between 25 and 34. Okay, that I just realized how that looked, how I wrote it. So I want probability that I'm going to have a value of X that's greater than 25 but less than 34. Okay. So on our distribution, we can say where is 25, right? Which we can generalize and locate, say, oh, 25 looks like it would be about there. Right, so we could say X at 25. And then let's use a different color. And we can say our other boundary of the area we're in search for is where X is equal to 34. Okay. So the actual probability or shaded area that I'm interested in finding is this part right here. Does everybody understand how that probability matches these expectations? Okay. So what do you think we do? Any ideas?
Find both z-scores.
Yep.
2 z-scores. Let's start there. Cut it off at that point. Okay. So 2 z-scores. So if we're finding the z-score of where 25 exists, right? That's 25 minus our mean divided by our standard deviation. Okay, and then somebody calculate these while I'm writing them. And then for 34, right, our z-score would be at 34 minus 27, right, or minus our mean divided by our standard deviation. So what did you guys get for z-score or z-score that's at a raw score of 25? Aaron, are those values the z's? Yeah, that would make sense. Wait, or are those the probabilities that you calculated? So
Yeah,
those,
he did the probability.
you did the probabilities. Okay, So we'll archive those for a hot minute. Okay. But if we do 25 minus 27 divided by 4,
negative left.
I got negative 0.5. Okay, and then 34 minus 27. Oh shoot, hold on. 34.
1.75.
That's what she is. 1.75. Okay, so now we have two z-scores. One's above the mean, one's below the mean. Okay, we know that the z-score, or the probability that we get when we get our this, right, that area for our z-score of negative 0.5, Aaron would be 30.85%, I'm assuming. Does anyone want to confirm that with a thumbs up? Okay, I'm looking at participant lists and not videos, by the way. So, okay, we've got lots of thumbs up. We can trust Aaron. Okay, so this percentage, if we're looking at it in terms of percentages, could be 30.85 or 0.3085. Either one is correct. Okay, and then our yellow shaded area, right, is everything that's to the left of the z-score at 34, which we are saying is 95.99%, which makes sense, right? So this yellow shaded area, I'm going to go this direction, right, is 95.99% or 0.9599 in terms of probabilities. Okay, but remember, I don't care about those individual ones. I only care about this area here. So how do I find that pink area? Subtract. Subtract what? The suspense.
The 0.9599 minus the 0.3085.
You got it, right? So in order to calculate this center portion, that pink portion, we have to take, right, the probability that we found from 34 across and then subtract the blue area, right? Because we don't care about that part. So by subtracting, we should get our pink area. So if we do 95.99 minus 30.85, and you can do this in terms of just decimal values as well, either way works. That should tell us what our percentage of values is within that pink shaded area. We got 30.85. So I got 65.14. Okay. 65.14 represents the probability that I'm going to get some random raw score between 25 and 34 in this distribution under the assumption that it's normally distributed. Have I lost anybody?
Where do you get 0.3085?
So that is from our Z table. And
Is it the same one in the lecture? Because I couldn't click the link. But
yeah, the one that the table that's like with the really, really small numbers.
mm-hmm.
Yeah, that's the table we're pulling from.
What do you look to get that?
So we need the area to the left of the curve at 25, and we need the area to the left of the curve at a raw score of 34, so that we take this yellow shaded area, subtract it from, do I have a pointer tool? I don't have a pointer tool. But
I get about that, but I just don't, because I'm looking at the.
The one in the lecture only shows the positive z-score.
Oh,
yeah.
Right.
That's
Oh, yeah. So there's two. In the PDF, there's a positive and a negative. Mm-hmm.
okay.
Yeah. And then finding the actual z-scores on the table makes sense though, right? Like how you look them up? Okay,
Yeah.
cool. Okay. But
I
generally,
also have a
go ahead.
question. Yeah, but since it's saying probability, when we have to like just divide it by 100 because then it'd be like 0.6514.
Mm-hmm. Yeah.
Got it.
So whenever you guys have like exams, usually if you have to do a calculation like this, I'll have a like a blank answer fill-in question. And I have a whole variation of answers between percentages and values between 0 and 1. So if you wanted to report this probability as, if you wanted to present that probability as a percentage or percentile, an acceptable answer would be 65.14. If you wanted to present it as a probability, then you could do it as 0.6514. But usually either way, I'll accept it either way. Okay. Does this process generally make sense though? Okay. So remember, the important thing to remember is that you're looking the z-score. Again, you have to assume it's normally distributed, and it gives you the area to the left of a given raw score of interest. Okay. To the left, just think Beyonce, right? Okay, I'm gonna stop sharing. We're gonna go back to the PowerPoint, and then we're gonna wrap this mofo up. Okay, what am I doing? Do it. Okay. Oh, okay, where'd my Zoom go? That's what I want. Okay, so we're gonna share desktop 2. Boom shakalaka. Okay, so let's go forward. These are some practice problems for you guys to work on. I have a video posted that goes literally through everything we just went through. Again, if you don't want to find it in the lecture video, minus the between and above examples that we did for percentages. But yeah, so if you want to take a screenshot of this, you can. The answers are also available in the short video that I do. But try to fill in the blanks on your own using our z-score formula and the z-tables, just so you have some practice working with those before you take the quiz, because there are questions where you might have to calculate stuff. Okay, but I'll leave those for you guys to work on independently. Okay, so any questions? Oh, actually, well, yeah, that's kind of a segue. Any questions on calculating z-scores or what they mean? I feel pretty confident in you guys. That's a good thing. All right, so z-scores can be used for other reasons. Okay, so one, we can use them to calculate percentiles, because we're looking at an area under the curve. We can also use them to create confidence intervals, which we'll talk about 3 weeks from now. Okay, and then the last thing, this is the this is one of the big calculations you really need to know how to do, and that's calculating skewness and kurtosis. And for some reason, it blows over almost everyone's head every semester. So I'm going to try my best to make it make sense. But we've kind of talked about skewness so far in terms of when we have extreme scores. So like negative skewness is when, think tail activity. Tails are what we're interested in. So actually I'm going to go to the next slide. So this is the only one we're looking at. Okay. Skewness is just looking at the symmetry of the distribution, right? So can we split it down the middle right? This red distribution is like our normal one. Can we split it down the middle, and is it symmetrical on both sides? That's what skewness is looking at, okay? When you have the presence of an extreme score, you can either end up with positive skewness or negative skewness, okay? Skewness, the sign of it is determined where the tail is located. So for positive skewness, I like to remember this in terms of where my standard deviations are. So my positive standard deviations are on the right side of the distribution. Negative standard deviations are on the left side, okay? In positive skewness, the tail is on the side above the mean, okay? So tail on it, you have some extreme score above the mean, right? Meaning it's on the positive end. Negative skewness is just the opposite, where you might have an extreme score on the negative side of the mean or below the mean, okay? So what does that mean in terms of your distribution, right? Because if you think of these smooth curves, if you imagine bars, right, that's like our frequency distribution. That indicates that there's a very low frequency of a given score out here, right? Or it could be underneath the blue curve, right? And there's more scores underneath these larger populated areas where the area is bigger, okay? So positive skewness, what happens when we have a tail that extends above the mean, we kind of talked about this last week, but the mean ends up getting drug towards the tail, okay? So instead of a perfect distribution where our mean, median, and mode are all equal to each other, what happens is this extreme score, because the mean is the most sensitive to extreme scores, that mean is going to get drug away from the peak closer to the tail, in which case the mean is greater than the mean, or the median and the mode, which should be still around this peak area, okay? If we flip the situation and we're looking at negative skewness, so that's my green curve here, right? Negative skewness tells me that the tail is below the mean of where below the center of the distribution, if you want to think about it that way, okay? And that means that I have a very low frequency at a score out in the distance away from where generally most of my scores have landed, okay? So what I want to do is figure out, well, how is that mean affected by that extreme score, right? Similar to how the mean gets drugged towards the tail in positive skewness, it also gets drugged towards the tail in negative skewness. So if you have an extreme score below the mean ends up getting drugged from its ideal position where the median and mode would be, and it gets taken down this direction, okay? So in that case, the mean would be less than the median and the mode. Does that make sense? Okay, so curve shape or distribution shape, that's what we're talking about, okay? So if I ever ask you guys like, hey, what does the distribution shape look like? Or what does the curve look like? You automatically think skewness and kurtosis. Kurtosis is the second part of this. So skewness is looking at how are we symmetrically placed, right, in our distribution? Do we have 50-50 on both sides of the center or no? Okay.
Natalie, could you pose a question? Like, how would you ask the question? Like the median this number, and there's this outlier that's really significantly lower. Which skewness would you use? And it'd be negative.
Usually I formulate questions either like what's happening to the measures of central tendency. So I could say if my mean is less than my median and my mode, that would indicate that I have negative skewness, positive skewness, or a normal distribution, and you would choose one of those three.
You said mean means less than?
Yeah, so in that case, we would have negative skewness.
Gotcha.
Mean gets drugged this way. So that's one way that I can formulate the question. And the same would go for kurtosis, which we'll cover in a second. Or I could ask you to calculate these things, which is the last part of the lecture. So I could say, based on your calculation, what is the shape of the distribution? And then based on the numbers that you get, you can say we have positive skewness, we have negative skewness, we have positive kurtosis, we have negative kurtosis, we have a combination of any of those things, or we have a relatively normal distribution.
Gotcha. Thank you.
Those are the two main ways I would ask. But this is only half of the shape, right? We also have to look at our tails in terms of what is the frequency on the kind of the outer regions. A lot of people like to look at kurtosis and say, look, the peak is really tall or it's really short, okay? And I have a way to remember this, but kurtosis is basically looking at the measure of the number of extreme scores. So what is the frequency of scores that lie in these outer regions? Because remember, when we look at shape, we're looking at tail activity. Okay, tails being the little swingy things towards the bottom of the x-axis. Okay, so positive kurtosis is identified by a tall peak and heavy tails. Okay, I know I just said you look at tails, but the way that I remember positive kurtosis is that you're like peaking, you're like super positive. I don't want to make the conversation about drugs, but you know, like you're like, whoa, I'm on top of the world, right? That positive kurtosis means that you have a really high frequency of values in the center of the distribution, and you have a very low number or low frequencies of a bunch of different outliers down at the end. Okay, so if the tails, this is the best picture I could find that does a representation of all of these, but don't imagine this tail hitting this x-axis entirely. Think of it just like floating above the top of it, right? And so that indicates we have this high concentration at the center and then a lot of outliers out on the edges, right? So instead of being nice and symmetrical, where we have a fairly spread out distribution, right, where 95% of our data is pretty well spread out, instead we have this high concentration in the center and a lot of outliers in the tails. Okay, so that's positive kurtosis. Negative kurtosis, the peak is flattened, so it's kind of sad and depressed towards the x-axis, right? But what that indicates is you can see there's higher frequencies in these outer regions now, right? And again, don't think of this as completely merging with the x-axis, but kind of floating above. And so these higher frequencies on the edges are going to indicate that we have few to no outliers, right? So in this case, we have light tails where they're kind of floating off of the x-axis, okay? So in terms of drawing this maybe a little bit better, think of positive kurtosis. Oh, there's the line. Got it. Okay, there was a delay. Think of positive kurtosis as looking something more like this. It's like an anteater hill. Okay, so this is positive kurtosis. Negative kurtosis, think of it more of being like this. Okay, so this was negative. Woo! Right? So this indicates there's a lot of outliers in positive kurtosis. Okay? Negative kurtosis, there's few to none. Right? Because the actual frequency, if we drew like a bar graph, the frequencies of all of these different points in this graph are almost equal to each other. Okay? which in our activity we'll kind of look at, are there sometimes, or do you have some times where you actually want this to happen? And are there some times where you want this to happen? Because there are, right? If we're looking at samples and we're comparing samples to each other, having some negative kurtosis might be a good thing, because that means that we have relatively equal sample sizes, right? So it's the shape of the distribution. The context of if it's good or bad is based on the actual question you're looking at, okay?
I have a question on this. What do the lines you just drew represent that connect like the x-axis to the top of the
those
graph?
are like if I had a frequency distribution made of bar graph, or like bars.
Oh,
It's a bar graph.
got it.
Mm-hmm.
And the other one's outliers, right?
Mm-hmm.
You're just saying, or no, or is are both of them just the bar graph?
Both of them are looking at outliers. How many extreme scores do we have, right? So the other way, I know some people think about it differently because automatically the eye draws to the peaks. So some people like to remember if there's a tall peak, it's a positive. If there's no peak, it's sad and it's negative. The other way you can think about it is positive means like there's multiple, right? So positive meaning there's multiple outliers, negative meaning there's few to none. That's another way you can remember it. Okay.
Okay.
But another way, we're looking at how many outliers do we have. Okay. Phew. All right. We're slightly running out of time, but I think we're almost done. We have 2 slides left, so we should be good. So this last part is calculating skewness and kurtosis. And I do have an example of this in the activity, so you'll get to practice in both Excel and SPSS. You'll get slightly different values between both programs, but I usually have both answers on exams. So you shouldn't be flagged if you use one method versus the other. But when we calculate skewness and kurtosis, we're comparing a sample to a population. Okay, or we want to know, is our sample normally distributed, in order to compare it to a normally distributed population? Because the population is golden, right? Population is always normally distributed. It's our samples that we have to evaluate. Like, did we actually collect a representative sample of the population? If it's a representative sample, it should be normally distributed. Okay, so remember, when we have this assumption of a normal distribution, we can use z-scores. Okay, so what we end up doing is we say sample skewness and sample kurtosis. So whatever the shape is in terms of the sample, we need to translate that into terms of a normal distribution, or in terms of a population, to see, is our sample similar enough to the population in order to consider the sample normally distributed. That's the whole point of statistics. We always want to see how closely the sample relates to the population. Okay, so in this equation, this top portion that we're looking at, so this sample skewness and sample kurtosis, those are for the sample itself. Those are like the raw values that we would get if we calculated skewness and kurtosis within a given data set that I hand to you guys. Okay. The bottom portion is the standard error of skewness and kurtosis. So that's this little square root of 6 divided by n and square root of 24 divided by n. These equations you definitely need to know, but again, they won't be paired with these words in an exam. Okay. But standard error is, without getting too much into it, because we will come back to this definition at a later time. If you think standard deviation is the deviation of some value x, so some measured raw score, and it's deviation away from the mean of a sample. Okay, so that's what standard deviation, and think of it in that's the terms that we use for a sample. For a population, we use the term standard error. So if you think a population is built up of a whole bunch of samples, right? And then within that population, if we took the means of a whole bunch of different samples and we plotted them, they should create a normal distribution, right? So if we pull a sample out and we want to see where is that sample located in the population, the standard error is kind of like how far away a sample mean is from the population mean, similar to how far away a raw score would be from a sample mean if we were looking at standard deviation. So a lot of times people get those two confused. And like I said, we'll talk about standard error more, but this is kind of how we relate the sample information to the population, right? By saying this is the sample skewness, this is the sample data we have, or kurtosis, and this is how far away it would exist if we had a population, okay? So we basically, by doing this calculation, we create a standard score, right? Or what we like to call in this class, the z-score of skewness or the z-score of kurtosis. I'll also refer to them as z-skew and z-kurt. They're like people, okay? But this is the method we're going to do in this class. And the nice thing is, like I said, you can do these calculations in SPSS and Excel because the actual numerator for this is kind of crazy. And it just doesn't make sense to present that to you guys. So I just put sample skewness. This is basically what Excel gives you and SPSS gives you. And then you can calculate the standard error separately. You just have to remember to piece together that sample skewness or sample kurtosis that you calculated needs to be divided by the standard error that is given to you by either SPSS or by calculations in Excel. Okay. So if we're talking in terms, if we're kind of drawing it back, our standard scores that we've reviewed so far are percentiles, z-scores, coefficient of variation, and then we have a z-score of skewness, z-score of kurtosis. Okay, anything attached to a z kind of falls into standard scores. Okay, so some notes on these equations. You can see that n is in the denominator, right, of a square root within a denominator. So its effects, usually when we see something in a denominator, we say, oh, it's indirectly related to whatever is on the other side of the equal sign. So in this case, if we have a small sample size, the likelihood of us having a high degree of skewness is pretty great, right? So that's another reason why we want a large sample size when we collect samples from a population for research, is that the bigger our sample sizes, the less chance we have of having skewness or having kurtosis, okay? Which again is evaluating the shape of the distribution, okay? Some other notes is that we use sample characteristics in the numerator, which I didn't show you guys, but sample characteristics are up here. And then results from the calculations are in terms of z-scores. So when we compare, and what's the best way to show this? I think I'm gonna switch to my whiteboard again, and then we'll stop after this because I know we're almost timed out and I've probably fried your brains into jello. So, oh, I have to share. Like, you guys can see this, right? Oh, okay. So very quickly, a note on statistical inference, basically. Let's say that this is a population. In a population, this shape is normally distributed. Okay, I'm gonna put ND because that's what normally distributed would be like. Who remembers what percentage of data lies between plus and minus 2 standard deviations?
95.
95.
95.
You guys are so smart. Okay. 95% of our data lies between plus and minus 2 standard deviations. Okay. So we could say if some sample that we throw into our population, we want to know where it's located, right? The chances of it being between plus or minus 2 is pretty good, right? Which means that, okay, well, we could probably accept that that sample is from that population. Okay. So when we do our statistics, let's say this is a sample, okay, and this is my mean. Whenever we do inferences from from a sample to a population, we have to say this sample mean, if we threw it into the population, right, we would hope that it's located somewhere between plus or minus 2 standard deviations to consider this sample a subset of the population, okay? If for some reason this sample mean, okay, our other options are that it lands outside plus or minus 2 standard deviations, okay? And so if that happens, then we say the sample is clearly different enough from the population that we have to consider that something is different about that sample. Maybe it belongs to a different population, okay? So when we're kind of using criteria for our Z skewness and Z kurtosis, you guys will get values that range anywhere between, well, typically between plus or minus 3, which would represent your kind of standard deviations, right? But remember, if this is a population, and if we have a sample that we're throwing into this, right? In this case, we're evaluating shape. So I'm just going to add that here. So instead of a mean, we just want to know if we threw this distribution shape into the population, would it land between plus and minus 2 standard deviations? Okay. So if shape being skewness and kurtosis, right? If either one of these, in terms of our little Z skew and Z kurt, if those values land between plus or minus 2 standard deviations, we say the shape is relatively normal. Okay. If these values from Z skew and Z kurt land outside, so if they're greater than positive 2 or they're less than, whoops, literally just wrote the same thing, less than negative 2, that means that they are negatively skewed or negatively kurtosed. That's on the negative side. Or if they're above, if they have a value above positive 2, that would be positive skewness or positive kurtosis. Okay, and we go into more examples in the activity, so that should start to make sense when you actually get into everything. But this is kind of the reasoning behind why we would accept if we have a relatively normal distribution shape for our sample versus if we're claiming that it's skewed or kurtosed in either direction. Okay. Does that make sense to people? I wish there was like a halfway thumb, but we got some thumbs up, so that's a good thing. Okay. All right. So that's all I have for you today. That's all. I like to go in depth on the normal curve just because it's such a huge part of the foundation of statistics and how we determine our interpretations of results and everything. But I will work on uploading the video to Beachboard, hopefully sometime, some decent hour for myself. But if you guys have questions as you go through the activities or quizzes during the week, let me know. Some of you have asked questions on quizzes. I don't mind helping you out on them as long as you've attempted the quiz at least once before you ask questions, okay? Which you would have to do in order to ask questions anyways. But try to troubleshoot through some stuff, send that my way, and then I can kind of help you figure things out from there. Okay. Any questions before we take off? I know I went a couple minutes over. I'm sorry.